We are in Unit 11 and this is Notes 4. Today we're going to do two more tests to determine convergence or divergence of series. And today we're doing the direct comparison test and the limit comparison test. So we're going to be using the comparison tests today. Okay? So let me introduce when you would use this. Let's say that we have this series that we'd like to see. They're asking, does this series converge or diverge? Okay, and let's say that we're given this. Okay, well, if we were given that series, it's not geometric, it's not telescoping. The nth term test, as n goes to infinity, this does go to 0, so we cannot use the nth term test. It's not, can we use the integral test? We could. We actually could use the integral test. The integral test, as you know from what you did yesterday, it's a little long. If there's another test to use instead of the integral test, I would rather use another test. Okay? So, and is this a p-series? It's not a p-series, is it? It's not because of the plus 5. If the plus 5 was not there, though, it would be a p-series, wouldn't it? Do you think the plus 5 would change the convergence or divergence down here? As it turns out, it would not. It would not change it. So, this is a prime example of when I would use a comparison test. And I would compare with the series of just 1 over n squared. I know that this converges because it's a p-series with p is equal to 2, right? So I know that this one converges. Therefore, this one has to converge as well. Okay? The only thing that I need to find out is which test do I use. Sometimes you can use either one. As it turns out in this case, you can use either one. Sometimes one of them is better than the other. Okay? So, here's some big old hair there. Okay, here's something to look at. So let's say, I should have left that in there. Okay. I want to show you graphically what's going on here. So I'm up in for y1, I'm going to put 1 divided by x squared, okay, where x is my n, even though this is a function, so it'll be connected, whereas this one is not connected. That's okay. I get the idea. In for y2, I'm going to put 1 divided by x squared plus 5, okay, and I think I'll turn on my little bouncies. So that I can really see it. Okay, I have my window set from yesterday. So there is 1 over n squared. It's going to 0, and it's going to 0 fast enough to converge. It's going to 0 fast enough to converge. Here's the 1 over n squared plus 5. It's also going to 0, isn't it? And it's always below 1 over n squared. So if 1 over n squared converges, it makes sense that this has to converge as well. Okay? This is a great example of when I would use a direct comparison test. So let's take a look at your notes that I gave you. Okay? So often we see a series that is similar to a p-series or a geometric series with a known convergence or divergence. These are usually quickly known ones, where you look at it and say, oh, it's just a p-series. Oh, it's just a geometric series. And you can get the answer really fast. Okay? So sometimes we see a series that is similar to one of those. Therefore, we are fairly certain we know whether it converges or diverges. When this is the case, use a comparison test. Right? 2 to choose from. Let's first look at the direct comparison test. So, This is the one that you're given in the problem, okay? The B sub n is what you're trying to find out. Does it converge or diverge? A sub n is what you're comparing it with. So this is what you're comparing with. All right? If this converges, and if every B is less than every B sub n is less than every A sub n, or equal to, then B sub n must converge as well. That's what we saw in this graph. If every B sub n is less than every A sub n, then B sub n, the series B sub n, must converge as well. Okay? Thinking opposite, okay, if this A sub n diverges, then we need for B, all of ours, to be bigger than every one of these, right? To say that it diverges. Okay, so if I graphed A sub n, and yes, it went to 0, but not quickly enough to converge, it diverged. If this diverges, and if every B sub n is bigger than every A sub n, so when I graph B sub n, it does something like that. So it's always above. Then clearly this must diverge as well, right? So greater than a diverging diverges. Okay? If I were to graph this one by hand, A sub n is converging, so this time this converges. And my one that I'm given, if it's always below, then clearly it must converge as well. Right? So less than a converging converges. Greater than a diverging diverges. And that is the direct comparison test. Now, one thing that we have up here, these are the conditions. Just like there are conditions for the integral test, you can only use a direct comparison test when all of your terms for these n values, all of the terms are positive or 0. They're greater than or equal to 0. So we must always state that. You must always state that. Just like you always had to state before you used the integral test, you had to state that the function was positive, continuous, and decreasing. You must state that all of your terms are greater than or equal to 0 before you can use a comparison test. Okay, let's take a look at some examples. Example 1. Okay, so first of all, what am I comparing it? What does it look like? What does it behave like? This behaves like, so I'm going to compare with the series for 1 over n cubed, because the plus 1 is not going to make a difference in the convergence or divergence of this series. So I'm comparing it with 1 over n cubed. What does this do? This is a converging p-series. Okay? I need you to tell me that converges and why. Okay? You don't have to do anything else, but just tell me it converges and it's a p-series. Okay? Now, before we use this direct comparison test, I need to say my conditions. So I need to state that 1 over n cubed is greater than or equal to 0 for n greater than or equal to 1, because I only need it to be true for these values, right? And 1 over n cubed plus 1 is also greater than or equal to 0 for all n greater than or equal to 1. Since those are both true, I can use a direct comparison test. To use the direct comparison test, Do you remember back in elementary school when you were comparing things? You would get like, your teacher would say, okay, 3/5 and 7/8. How do they compare? And you would have this circle here. And you would fill it with either a less than sign, a greater than sign, or an equal to sign. Well, that's what we're going to do here. We're going to fill in this sign with either a less than or a greater than. They will never be equal to. Because if they were, then you wouldn't be doing a comparison test. You would just be going over and answering it as the P series or Geo series or whatever. Okay? So, which is bigger? Which is bigger? This denominator has this plus 1. This denominator is always larger than this denominator, isn't it? The denominator is always larger than this denominator. Always, for all n. Therefore, 1 over this will always be less than 1 over n cubed. Always. It makes sense. If you look at the denominators, if you keep the numerators the same and only look at the denominators, it's really easy to compare these two. If this denominator is larger than this denominator, then the whole fraction will be less than this fraction. So we have a series with terms always less than a converging, and less than a converging series converges. So I will say that my series converges by direct comparison. I'll just say direct comp with 1 over n cubed. Tell me what you're comparing it to. I will see it. I will see it here. So you don't really have to say it again here, but you do need to say converges by direct comparison. Okay? All right, next example. What does this one behave like? Well, this one behaves like, so we're going to compare with 1 over 3 to the n. Okay? 1 over 3 to the n. All right, so what does this do? This is a geometric series. R is 1/3. So this is a converging geo. Okay? Condition time. 1 over 3 to the n for n1 to infinity is always greater than or equal to 0. 1 over 3 to the n plus 2 is also always positive for n greater than or equal to 1. So I can use my comparison test. So for the comparison test, I simply take what I start with, the terms I'm starting with, compare it against what I'm comparing it with. If your denominators are the same, all you have to do is look at your denominator. If your numerator, I said that wrong, if your numerators are the same, all you need to do is look at the denominators. This denominator is larger than this denominator. So this fraction will always be less than 1 over 3 to the n. So we have something that's less than a known converging, and less than a converging converges. Converges by direct comp test. Okay? You can say with 1 over 3 to the n. Most kids like to say that, but I can see what you compared it with here, so you don't have to say it again here. I already know. You already said it once. Once is plenty. But if you'd like to say it again, that's fine. I won't get mad. Okay, we're going to try to squeeze in number 3 over here. I didn't give us much room, so I'm going to come up and use some of this space up here. All right, so what are we comparing it with? get back my orange here, I think. Let's compare with 1 over square root of n. This is a p series. P is a half. So this is a diverging p series. P is a half, right? Less than 1. Okay, now I need my conditions. All right, so 1 over square root of n. For n 2 to infinity, for 2 to infinity, this is always greater than or equal to 0. For n greater than 2. And 1 over square root of n minus 1 is also greater than or equal to 0 because n starts at 2. Okay? So it's also greater than or equal to 0. Okay? So we can compare. I write down what I'm trying to figure out. I compare it against what I know. All right. The numerators are the same, so just look at the denominators. This denominator on the left is always less than the denominator on the right. So the fraction, this fraction will always be larger than this fraction. So our series is greater than a diverging series. So if our series is greater than a diverging series, then our series must also diverge by direct comparison with 1 over square root of n, if you want to say that. Okay? All right. Now, what if? What if, this is usually where, but Miss Murray, what if, and this leads great into what we're about to do. What if we had this series? I would need to make this something like a 2 if we did that. Otherwise, my first term would be undefined. So we'll do that. Okay? What if we had that series? I would still want to compare it. I know it behaves like 1 over n cubed. I know it does. So I know it's going to converge. But when I do the comparison, what happens? This denominator is always less than this denominator, so the whole fraction will be bigger than. And I have a series that's larger than a converging series. Can I use direct comparison for that? No, I cannot. I have this series that converges, and I have this series that's always above it. I know nothing about this one then. Okay? So I cannot use direct comparison in this case. I need to use limit comparison. So here comes the limit comparison test. Okay. Our conditions are the same. Conditions are the same. If the limit of a sub n over b sub n is equal to L, where L is both finite and positive, then our two series both converge or both diverge. Okay? So, this looks weird, but it's actually very, very good and easy to use. Okay? This is one I actually prefer to the direct comparison test. To me, it's very obvious. Okay? And after you do a few problems, I think that you'll see what I mean. Okay? So let's take a look at A. So A looks unpleasant. Do you agree? It looks unpleasant. But let's simplify things. Let's simplify things. as n goes to infinity, the plus 10 doesn't matter. And in the bottom, only the highest degree term even matters. It's the only thing that matters. The n cubed and the 7, they really don't matter. So this behaves like n to the 4th over 4n to the 5th. That's what it behaves like. So I'm going to compare with what does this reduce to? What does n to the 4th over 4n to the 5th reduce to? Well, it reduces to 1 over 4n, doesn't it? Do you agree? It reduces to 1 over 4n. I'm just going to compare it with 1 over n. You could compare it with 1 over 4n, and you get the same answer. But I'm just going to compare it with 1 over n. Okay? That's my harmonic. This diverges. It's the diverging harmonic. Okay? Now I need my conditions, so I will state that 1 over n is greater than or equal to 0 for n greater than or equal to 1. And I don't want to rewrite this all, so I'm just going to call that a sub n, and I'm going to say a sub n is also greater than or equal to 0 for all n greater than or equal to 1. Okay, and you know what? Do I know that for sure? I see a minus in here. Do I know that it's always positive? I'm just going to tell you right now, you guys, nobody's going to try to trick you and give you something that's going to be negative in there, okay? So just assume that I've done the legwork ahead of time and it is positive. I need you to state these conditions, though. I do. This is something that I didn't used to do. I didn't used to have my kids state this, but there was a question on the AP test, and it said to state the conditions for this. And my kids didn't know what they were because I didn't make them. They learned it when we did the test, but I didn't make them write it each time. And so very few of them got that right because I didn't make them do it. So I do make you do that, and I do it so that you will, if it happens to be on the AP test, I don't want to be the reason that you don't get that point, okay? So state these two, but know that they are going to be true. You don't have to worry about it, okay? All right, so now we do the limit. Limit as n goes to infinity. Limit as n goes to infinity. And we're going to put, I like to put the more complicated thing on top. It doesn't matter. Do not worry about, oh wait, which is A and which is B. All we care about is that we get a finite positive number. We don't care what the number is. All we want is it finite and positive. Finite means it's not infinite. Positive means it's positive. So you're either going to get a number or 1 over that number, and that's not going to change whether it's finite or positive, right? So it does not matter which you put on top here. I prefer to put the more complicated thing on top, and you'll see why in just a second. So I'm going to put the complicated thing on top. Okay? And I'm going to put the less complicated thing, 1 over n, on the bottom. So what I have here looks rather awful, but it's really not, because we just have a complex fraction. And this 1 over n, I can change to multiply by n over 1, right? Or you can think of that as multiplying top and bottom by n. And when you do that, you get n times n to the 4th plus 10n over that denominator all over 1, right? What's this limit? As n goes to infinity, the 10n doesn't matter, the n cubed doesn't matter, the plus 7 doesn't matter, none of that matters. The n to the fifths reduce to 1, and you're left with 1/4. Is 1/4 finite? Yes, because it's not infinity. Is 1/4 positive? Yes. So I write finite, positive. Check. So whatever this does, this does. Okay, so my series diverges by limit comparison test with 1/n. Okay? So when you look at this, think, those don't matter. Compare it with 1/n. I know it's going to diverge. I know it will. Just prove it. Let's do this one. All right. So we're going to compare with what? What does this behave like? 1/n cubed. Behaves like 1/n cubed. Okay. What does 1/n cubed do? Well, it converges. It's a converging p-series. Right? Okay, state your conditions. 1/n cubed is greater than or equal to 0 for n greater than or equal to 2. And 1/n cubed minus 2 is also greater than or equal to 0 for all n greater than or equal to 2. Go to your limit. The limit as n goes to infinity of your more complicated thing over your less complicated thing. By the way, back here, we got 1/4 for that limit. If we had flipped these, we just would have gotten 4 for the limit. It was still finite and positive. So it truly does not matter which goes on top. It just is a little easier if you make your more complicated thing on top. So 1/n cubed minus 2. Okay, now be careful. Watch this. I want to divide by 1/n cubed, right? Which is the same thing as multiplying by n cubed over 1. Go ahead and do it now, and it'll save you one step. You're dividing by 1/n cubed, which is the same thing as multiplying by n cubed over 1. And now, you got n cubed over n cubed minus 2. What is that limit? That limit is just 1, right? Because the minus 2 won't matter. Got n cubed over n cubed, and that reduces to 1. Is 1 finite? And is it positive? Yes. So I'll say finite, positive. So our series does whatever this series does. It converges, so our series converges by limit comparison test. Okay. Next one. What does this compare with? Look for your highest degree on top and your highest degree on the bottom and reduce those. That's what you compare it with. So we're going to be comparing it with 1/n squared, n cubed over n to the fifth. This converges because it's a p-series with p is 2, right? Okay. This is a big thing, so I'm just going to let that be like a sub n or b sub n, it doesn't matter. And then I'm going to say a sub n is greater than or equal to 0 for n greater than or equal to 2. And 1/n squared is also greater than or equal to 0 for all n greater than or equal to 2. Time for our limit. limit as n goes to infinity of our more complicated divided by our less complicated. Divided by 1 over n squared is the same thing as times n squared over 1. Right? So when you multiply in your n squared, you're going to get 2n to the 5th minus 3n to the 4th plus 8n squared divided by n to the 5th plus 2n to the 4th minus 9. What's that limit? These don't matter. The n to the 5ths reduce out, and you're left with 2. Finite, positive. In the limit comparison test, that's what you're looking for. Is this limit finite and positive? Yes, it is. So this does whatever this did. This one converged, so ours converges. Converges by limit comparison test. Okay? That's the limit comparison test. So limit comparison test I like to use when I have polynomial over polynomial. I like to use it then. It also works good. It works good with p-series. I like it for p-series, comparing it with p-series. We could have used the limit comparison test. We could have used it, I think, for every one of these as well. Okay? So the limit comparison test would have worked for those. But the direct comparison test, this would have been kind of a nightmare. These two would have been kind of a nightmare to use the direct comparison test with. And this one, the direct comparison test would have failed. So we can't use it there. Okay? All right. Those are the comparison tests. Go practice them. Sometimes, these examples were fairly straightforward. Sometimes it's a little bit harder to come up with what you want to compare it against. Okay? So go practice. There are some on your worksheet that they're a little bit more challenging, but that's okay. It's all right. See what you do on them. Okay. Have fun.